We're given matrix A, which is a 4x4 matrix, and we're asked to find the eigenvalues of A. The eigenvalues of A are the values of lambda that satisfy the equation the determinant of the difference of matrix A and lambda times I equals 0, which can also be expressed as the determinant of the difference of lambda I in matrix A equals 0 as shown here. Let's go ahead and use this form of the equation. And I've already set some of this up. We have the determinant of this difference, where this matrix here is lambda times I, where matrix I is the 4x4 identity matrix, and then here's matrix A, the given matrix. So we want to find the determinant of the difference of these two matrices, which gives us this determinant here. So we want to find the values of lambda that make this determinant equal to 0. To evaluate the determinant, we'll use the cofactor method, and it would be best to select the row with the most zeros, but in this case, because all the rows contain 2 zeros, let's go ahead and use row 1. Starting with row 1, the first element is lambda plus 3, so we have the quantity lambda plus 3 times negative 1 raised to the power of the sum of the row and column of this element, which is in row 1, column 1, 1 plus 1 is 2, times the determinant formed by eliminating row 1 and column 1, which will give us a 3 by 3 determinant, where the first row would be lambda minus 4, 0, 0. Second row is 0, lambda plus 5, 4. The third row is 0, 2, lambda minus 2. And then we have plus the next element in row 1, which is negative 2. So we have plus negative 2 times negative 1 raised to the power of 3. Because this element is in row 1, column 2, 1 plus 2 is 3, times the determinant formed by eliminating the row and column of negative 2. So we eliminate row 1, column 2. The remaining elements make up the determinant, so we have 3, 0, 0, 0, lambda plus 5, 4, and 0, 2, lambda minus 2. Now we can actually go ahead and stop here, because notice how the remaining elements in row 1 are 0, so the rest of the expansion would be 0. So we want to know when all of this is equal to 0. So now we need to evaluate the 3 by 3 determinants, and again we'll use the cofactor method. So negative 1 to the second is positive 1, so we have the quantity lambda plus 3 times, let's go and expand using row 1, so we have the quantity lambda minus 4 times negative 1 to the second, because this element is in row 1, column 1, times a 2 by 2 determinant, which is called the minor, formed by eliminating row 1, column 1. So we have lambda plus 5, 4, 2, and lambda minus 2. And again, notice how the remaining elements in row 1 are 0, so we can go ahead and stop here. The rest of the expansion would be equal to 0. Here we have plus negative 2 times negative 1, that's positive 2. So we have plus 2 times, let's use the cofactor method using row 1 again, so we'd have 3 times negative 1 to the second, because this 3 is in row 1, column 1, 1 plus 1 is 2, times the 2 by 2 determinant, formed by eliminating row 1, column 1. So we have lambda plus 5, 4, 2, lambda minus 2. And once again, the remaining elements in row 1 are 0, so we can go ahead and stop the expansion. So all this on the left must equal 0. So for the next step, we'll evaluate the 2 by 2 determinants by finding this product minus this product. Let's do this on the next slide. So we have the quantity lambda plus 3. Let's go ahead and use a bracket here. And then we have negative 1 to the second, that's positive 1. So we have lambda minus 4 times the value of the determinant, which is the quantity lambda plus 5 times the quantity lambda minus 2. And then minus 4 times 2, which is minus 8. So we have a closed parenthesis here, then a bracket. And then plus 2. Let's use a bracket here. Then we have positive 3 times the value of the determinant, which again is the quantity lambda plus 5 times the quantity lambda minus 2 minus 4 times 2 or minus 8, and then all this equals 0. So for our next step, let's go ahead and simplify here and here. So we have the quantity lambda plus 3 times, we have lambda minus 4 times, here we're going to have lambda squared, and then minus 2 lambda plus 5 lambda, that's plus 3 lambda, and then we have negative 10 minus 8, which is minus 18, plus 2 times the quantity 3. Now this is the same expression as this expression, so this is going to simplify to the quantity lambda squared plus 3 lambda minus 18. Now we're actually going to factor this. Notice how this product and this product contain a common factor of lambda squared plus 3 lambda minus 18. So we're going to go ahead and factor that out. So we'd have lambda squared plus 3 lambda minus 18. Now let's be careful with what's left. If we factor this factor out of this product, we would have the quantity lambda plus 3 times the quantity lambda minus 4, and then we'd have plus, if we factor this trinomial out of this product, notice how we have 2 times 3 left. So now for our next step, let's go ahead and simplify inside these parentheses here. So we have lambda squared plus 3 lambda minus 18 times, here we'll have lambda squared, and then minus 4 lambda plus 3 lambda, it's minus 1 lambda or minus lambda, and then 3 times negative 4 is negative 12, but then we have plus 6, so minus 6 equals 0. Both of these trinomials will factor into 2 binomial factors. The factors of lambda squared are lambda and lambda. The factors of negative 18 that add to positive 3 would be positive 6 and negative 3. And now for this trinomial, the factors of lambda squared are lambda and lambda. The factors of negative 6 that add to negative 1 are negative 3 and positive 2. So this product equals 0 when lambda equals negative 6, when lambda equals positive 3. Notice here we get another lambda equals positive 3, and here we get lambda equals negative 2. So we actually have 3 eigenvalues, even though the eigenvalue of positive 3 has multiplicity 2. Let's get these in order from least to greatest. So we'll say lambda sub 1 equals negative 6, lambda sub 2 equals negative 2, and lambda sub 3 equals positive 3. But let's go ahead and make a note here. This eigenvalue has multiplicity 2. I hope you found this helpful.